Wednesday, when we were so rudely interrupted, we were starting to talk about chemical equations. And chemical equations, that nice shorthand notation that essentially tells us what the chemical change is, what the chemical reaction is. And the other piece that I mentioned was that chemical equations must be balanced. So the atom counts in the reactants must match the atom counts in the products. To make sure this happens, we're going to use coefficients. To multiply to get that atom balance. They're used as multipliers to achieve that balance. When we write down our chemical equations, we're always going to have our reactants, our starting materials, going to form our products. This reaction arrow here, you can think of it as a chemical equal sign. So that's where we're talking about coming up with that atom count. I'm going to show you first an unbalanced equation, and then we're going to do a balanced equation. For what we're doing right now, I want you to be able to determine counts of the various elements to see if an equation is balanced or not. I'm not worried yet about if you can come up with the coefficients. We will do that later. So right now, we're going to build the skill of atom counts. To see if we have a balanced equation. Okay. Unbalanced expression number 1 is the formation of ammonia from its elements. So that would be N2 plus H2 goes to make NH3. And some of you may already look at that and recognize that the number of N's is different, and all of a sudden we go from H2 to H3. And that is exactly the point. When we have something that is unbalanced, we have unequal amounts of the various types of atoms. Eventually, our goal is going to be to make them equal. First thing to do is just to learn how to pick apart these various chemical formulas. So in N2, there are 2 nitrogens, and in H2, there are 2 hydrogens. On the product side, I only have 1 nitrogen, and I have 3 hydrogens. These counts do not match. Because they don't match, indeed, that equation is not balanced. Let's show you what it looks like balanced. So balanced out, it's going to be N2 plus 3H2 goes to form 2NH3. And now we're going to go ahead and we'll do this atom count again. This time, hopefully it's going to come up. Everything is nice and balanced out. So again, got the 2 nitrogens. Now I don't have 2 hydrogens. I actually have 6. If you'll allow me to do a little bit more of a pictorial representation of what this 3 means and what that 3 means, and my implied 1 here. So it's telling me that I have N, and then for my 3 H2s, it's telling me that I have H connected to H connected to H, I have to, and H connected to H. Each one of these is H2. I have 3 of them. So there's 6 of those H's total. And finally, on the product side, I have N connected to 3 H's, and I have 2 of those. That means that 2 hydrogens and, 2 nitrogens and 6 hydrogens. So my coefficient, I will distribute through. And these are multipliers. Let's look at another unbalanced. All right, for this unbalanced, it's going to be Fe NO3 and K2SO4 going to make Fe2SO4 3 and KNO3. Same as we did before, make a list of all of the elements that are present. And to do this, I'm just going to walk us through the elements on the reactant side. So I have Fe, N, K, whoops, just go in order. FeNO, K, and S. And now I get to count. Well, the 3, this subscript 3 involves just what's inside the parentheses. That means that there's only 1 iron. I'm going to take the 3 outside the parentheses and I'm going to distribute it through. So I have 3 nitrogens, and I'm going to put off to the side here for my oxygen count. I have 9 of them from that FeNO3. And the reason why I'm putting it off to the side is because of the potassium sulfate, the K2SO4. There's oxygens there. So I have them in 2 compounds. So I have whatever is from the iron 3 nitrate, and then I have what's from the K2SO4. Because I don't have any parentheses in that K2SO4, that means that there's just 4 oxygens there. That gives me 13 total. And then let's see, I have 2 potassiums, and just 1 sulfur. And we'll do this exact same thing on the product side. I have 2 irons and nitrogen. I'm only going to have 1. Oxygen, I still have it in 2 places. This 3, I'm going to, again, distribute through everything inside those parentheses. There's 3 of those SO4s. So that means I've got 12 oxygens from the Fe to SO4 3. And then there's 3 more from the KNO3. So there's 15 total. For the potassium, there's 1 of them. And for the sulfur, there's 3 of those. I walked us through figuring out if, pointing out every single atom count. If on a homework assignment or on an exam, it says, pick out the balanced chemical equation below, and the first count that you do is for the iron, it's already unbalanced. So I already, just by looking at the iron, know that it's unbalanced. I don't need to balance all the rest of those atoms. I don't need to check them. If one element's atoms don't balance, then the whole thing is off. You might as well just forget doing it. Okay? Now, if I want you to prove to yourself that this is the balanced equation. And that's going to be 2 Fe NO3 plus 3 K2 SO4 going to make Fe2. And let me rewrite that one, sorry. So 2 and SO4 3 times, and then 6 KNO3s. Yes. Prove that to yourself that it's balanced. Chapter 3 goodness. Chapter 3 goodness is all about measurements. And how do we handle numbers in terms of chemistry classes? First off, remember we are delving through chemistry and it is an experimental science. And being an experimental science, being a science, it is based upon observation. Observation is how we gain information. As we're going through, you'll find out that we will be talking about both qualitative observations and quantitative. These qualitative observations are simply made through physical senses. You can use pieces of equipment and make observations with pieces of equipment. The only thing is that you're not going to be looking at exact numbers. Think about when you had your temperature probe plugged in during the first lab and you pinched the thermometer probe and you saw that the temperature started to increase. You would just look at the numbers and they would go up. That is still qualitative. You're looking just at a trend. The trend goes up, the trend goes down. You weren't making numeric observations in that, oh, the temperature started at 21.6. I got the temperature up to 23.4 degrees Celsius. That's not, just did it go up or did it go down? Quantitative would have involved looking at the actual numbers. Where did you start and where did you end? Numerically, what was the temperature difference? So these quantitative observations you got to have some sort of numerical measurement. When you communicate these quantitative observations, there's two parts that you must communicate. All right, so got to have two pieces. Piece number one, you have to have the number, the magnitude, if you'd like. How big? How small? How much? The second piece, you must include a unit. The unit gives you context. The type of measurement. Am I talking about, well, we'll put it this way. Let's suppose it was 73 out. Okay. Do I need a coat? Do I need to wear a jacket? The answer is no, yes. Don't bother, you're dead. All right, that's a little bit of a horrible joke, I admit, but here's the deal. When I mention it's 70 out, my mind automatically goes to 70 Fahrenheit, 73 Fahrenheit. No, I'm probably not going to be wearing a jacket. It's reasonably warm. It's nice. I'm not going to wear a jacket at 73 Fahrenheit. If it's 73 Celsius, I'm cooking. I'm hot. Water boils at 100 degrees Celsius. Our body temperature is 37 degrees Celsius. So 73 degrees Celsius is incredibly warm. Flip it to the other side, there is another temperature scale called the Kelvin scale. The Kelvin scale, you take your temperature in Celsius and you subtract 273. So let's see, 73 minus 273 puts me at -2, or I'm sorry. Let's try this again. Oh, so Kelvin is 273 minus degrees Celsius, so 200 Kelvin. 200 Kelvin minus 73. That's pretty much about the temperature of dry ice. Really freaking cold. Really, really cold. Or 73 Kelvin would be negative. I'm sorry. Let's do this. So if I had, my temperature is 73 degrees Fahrenheit. No jacket. -73 degrees Celsius. Way hot. 73 Kelvin. Well, that would be -200 degrees Celsius. And I take it back, that is liquid nitrogen type temperature. So incredibly cold, freeze you, freeze your skin, extreme frostbite, just not a good idea. So the question of, do I need a jacket or not, all depends upon what unit. My very first cat, rest her fuzzy little butt, same cat. She was 22 and she was 6 when she crossed over the bridge, the Rainbow Bridge. 22-6. Win-loss record? Probably not. 22-pound cat at 6 years old? Maybe. I don't know. 22, is that human years? I don't know. She was 22 years old and she weighed about 6 pounds. Without me being here to tell you that those numbers are meaningless. We will get to this idea of units. Before we get to units, I want to look at what are called significant figures. And significant figures come about because every measurement let's try this again. Every measurement and calculated result based on measurements have some uncertainty. And so there's some uncertainty with those. There's two things that we need to do because of this. One is we're going to want to communicate which digit is uncertain. We also are going to want to, when we round an answer, we want to reflect that uncertainty. You can't be more sure of an answer than you are of your starting point. So I have an example here, and you're going to have to bear with me because I'm going to be drawing some lines, and hopefully the iPad doesn't go nuts as I do this. So let's look at some lines here. Okay, that's good. That is good. Loving it. Nothing like a big old zoom. All right. Okay, so let's see. And for this exercise, I'm not concerned at all with the unit. It's just some measurement, okay? And I've chopped out the rest of this measuring device. What do you know? What do we know? We know the end of that line is between 5 and 6. Anything more than that is going to be a guess, is going to be an estimation. But I want you to estimate. Well, it seems to be less than halfway. So an estimation of something bigger than 0.5 doesn't seem quite right. Maybe 5.4, 5.3, maybe. Maybe 5.2. So I'm going to have you estimate to the 0.1 place. So you might end up with, again, 5.2, 5.3, 5.4, and I'm just going to highlight those are your estimates. Okay, I'm going to redraw this little picture. No, that's not what I wanted. That was actually what I wanted. Come here. There we go. Okay, so let's see, I've got here we go again. I'm going to go get a new ruler, okay? And this time, this ruler actually has some nice subdivisions, which is pretty cool. And now let me put in my happy little piece here. Supposed to represent the same thing. Still have this as 5, and I have that as 6. But now I know for sure that not only is the end of this little purple line between 5 and 6, now I can maintain, yeah, it's between this mark and this mark. I know that for sure. So I know that it is so I know it's between 5.2 and 5.3. Since I know to the 0.1 spot, I'm going to estimate the next spot over. So we're going to go to the 0.01 place. And I'm going to guess that most people are going to start to give me numbers like 5.298, or I'm sorry, let's try that again, 5.29, or maybe 5.28. And if you were sitting off to the side in the classroom, I might have been able to convince one of you to give me a 5.27. But again, I know the 5, I know the 2, and now I'm going to estimate. One last time, I promise. Okay, let's see here. Sorry. Okay. There, there. How did I do that? I didn't go out far enough, apparently. Okay, let's try this. Okay, now, now I have this at 5.2, and over here I've got this at 5.3, and I can make those marks just a little bit bigger. There we go. Now, what do you know? Well, let's see. I know that the end of that line, without a shadow of a doubt, is between those two marks. So we know the end is between 5.28 and 5.29. This means that we're going to now estimate one place over. So I'm just going to be thinking about at what place I'll be making that estimation. And once again, it's the exact same process. Let's see, 5.28 what? Okay, so maybe 5.288, 5.287. I don't think 5.289, but that might be your estimation. I would be really happy with anything that was higher than 5.285. I'll be really honest. This notion of having digits in a number that you know for sure, I know those, and there's my guess, is what's called significant figures. And that's what we're talking about on Friday.